a few words about units of these new rotational variables, theta, omega, and alpha, which often confuse students when they're working on problems and thinking about the theory here. Consider a fan blade then, and one of the examples that we sort of hypothesized we might be interested in. There's a fan blade sort of turning, say, in this direction here, and there's a dot on one of the fan blades, and the dot moves from position A to B. In other words, the fan blade starts to rotate like this. So this fan blade, which is right here, sort of in the top, so this fan blade right here, what would happen if it sort of rotated down to this position here? So the whole thing sort of moves down. How would you characterize what theta would be? Well, one way I'd characterize that is just say that theta is 90 degrees. And by just saying that, I'm saying, well, this is straight up, maybe some reference angle of 0, and if it moves all the way down to here, that's 90 degrees. And that would be a good way of characterizing the motion. You might say that the fan blade is rotated by 90 degrees. So right off, you see that the degree here is a good unit for theta. But the units sort of go on. In other words, if you sort of work through problems and things like that, you'll find theta it can be in degrees. You can certainly describe it as degrees, but you could also use radian measure to describe how far this dot moved on the fan blade. So in other words, if it's 90 degrees, it could also be described as, say, pi over 2 radians. That would be the same thing, because pi over 2 radians is another way of measuring an angle. So see, right off, there's two different units for theta. You can measure it in degrees, you can measure it in radians. Another unit that comes up a lot for theta is in revolutions, or just revs, or something like that. Revs for short. Because you could also say the dot went from here to here, that's 90 degrees or pi over 2 radians, but it also looks like a quarter of a revolution. 1/4 of a revolution. So you see, just in this simple example, I have three completely different ways of describing the angle through which this purple or black dot or whatever has rotated on the fan blade, and it can be done in degrees, radians, or revolutions. All of them are acceptable. So what's important in a case like this is that you're comfortable both in using the units and converting freely between them so you can adapt problems as needed. So here's a few conversion factors you definitely know, so you can just use them. So for instance here, we know that 1 revolution, which is what happens when an object like something circular like this, say there's a dot on it, spins all the way around. That's 1 revolution. That's equal to 360 degrees. There's one conversion factor for you there. And we also know just from geometry here, or trigonometry, that 360 degrees is equal to 2 pi radians. So there's a conversion between degrees and radians. And of course you can cancel out the 2, and maybe just remember that 180 degrees is equal to pi radians. So these are two conversion factors that if you have these things here, you can sort of never go wrong. You can always adapt a problem to be in whatever unit you need it to be in here. And I'll just say that and when you're working physics problems, say from the back of textbooks, they're often quoted in revolutions because it's such a convenient unit, but often radian is the better unit to work. In other words, the radian is sort of the SI unit then for rotational distance, and so you should focus on getting all your variables in radians. I strongly recommend it. What about the other variables then? Well, if theta can be measured in degrees, radians, or revolutions, what about omega then? What units would it have? What units would it have? Well, in general, omega is something like the change in the angular position over change in time. Now, there's an equation for it and so on, which was covered in another video, but this is generally the definition of omega. And so as you can see then, the bottom is always going to have some units of time, whatever time interval you want to measure it in, and the top is always going to have the units of what theta is. So the top could be in degrees, in radians, or in revolutions, anything like that. So when you're looking at omega, you're looking at something which is degrees per unit time, radians per unit time, or revolutions per unit time. What do you typically see in problems? You'll see degree per second. You'll definitely see radians per second, because this is the SI unit of angular speed there, radians per second. And a lot of times, you'll see something that's in RPM. Now, an RPM is something that comes from automobiles and stuff. It's a very convenient rotational speed variable to use. And, of course, it stands for revs per minute. So if you ever drive a stick-shift car, often you look at the tachometer, you're shifting from first to second after 1,500 or 2,000 revolutions per minute, something like that. Or you could characterize a drill or something traveling so many revolutions per minute. And it's a very convenient unit for humans to use because you can always visualize something. Like if I tell you a fan blade is rotating at 10 RPMs, you can sort of visualize a blade going around 10 times in 1 minute. But the other units aren't so easy to sort of visualize like that. But nevertheless, you just have to be able to interconvert between them. And let's just look at one example here. Hopefully you can think of these interconversion units here, these conversion factors in particular, the revolution of degrees, just like the conversion factors you're used to, like that, there's 12 inches in 1 foot, or 100 centimeters in 1 meter, you know, that kind of thing. They're just conversion units that you use to move between these different units of measure here for angles. So just as one example to start with here, suppose there was something about a drill that was traveling at 2,000 RPM, and you wanted to get those units in radians per second, because that's a better unit to work in for your equation stuff. Well, you just start using the conversion factor. So you write the 2,000 RPMs as revolutions per minute, get a full fraction there so you can sort of analyze how the units are going to cancel, and then the next thing you do is you sort of multiply that by something like 1 minute in 60 seconds. That will convert the time base. How do you get rid of the revolutions? Well, as you know, there's 2 pi radians in 1 revolution. So what you're looking at for something like this is multiplying. You start with the 2,000, divide by 60, multiply by the 2 pi, and for this I'd get something like 209 radians per second. And so that's what I'd get converting 2,000 RPMs into radians per second. 2,000 RPMs is something like 2,009 radians per second. So you can see the convenience of the units then. 2,000 RPM is something that's pretty fast, but at least you have a mental grasp. You can just imagine or think of something traveling 2,000 times around its orbit or circle per minute, 2,000 times per minute. But in terms of calculations, the number that's most convenient to use for you then is 209 radians per second. Now I look at this number and I have no idea what it means. Is it fast or slow or what? I have no idea, but it is the conversion. But that's why the RPM sort of sticks around, because it makes some good common sense to us. 2,000 revolutions per minute is something we can grasp. 2,009 radians per second perhaps is not. Lastly then, it's probably going to be obvious to you, what about the units of good old alpha, the angular acceleration? Well, once again, the units of alpha basically come from the change in the angular speed over time. So you'll take the units of the angular speed and divide by another time unit once again. And so you'll get something like, it'll be a degree per second, a radian per second, or a RPM, once again divided by some time unit here. So that's what gives the time unit squared in the bottom. So often the units you see for alpha then will be in numbers like radians per second squared, degrees per minute squared, or something like even a rev per second squared, anything like that. Just strange units, but when you see units of basically something that resembles what theta would be on the top and a second squared in the bottom, you know they're always talking about the alpha down there. And if I were you, I'd be very careful and always get my alpha in terms of radians per second. And one more thing to say about that, because the conversion to radian per second can often be just a tad bit confusing. So let's just maybe look at how one might get set up then. So suppose you're working on a problem and it says something like there's an alpha, an angular acceleration of an object, which is something, let's just choose a nice round number, like 10 revolutions per minute squared. Okay? So something that is incredibly hard to grasp. I have no idea what this really means, but the angular speed of the object is increasing by 10 revs per minute every minute, say. That's what alpha means there. How would you convert this into radians per second? Well, you have to be a bit careful here. The first thing is let's get rid of the minutes squared. So the only conversion factor I know between minutes and seconds are the fact that every 1 minute represents 60 seconds. But just note here that this isn't quite enough, because there's a minute squared here and only a minute here, so you don't quite get the cancellation of the units. But what you do is just square this entire quantity here. Because if you can multiply by 1 minute over 60 in terms of units conversion rules, you can certainly multiply by 1 minute over 60 seconds and just square the thing, because remember, this conversion factor here is like 1 because the units make it work out. So you just have to square it. Now I'll have a minute squared, which will cancel that minute squared, and I'll get my problem to work out. And last, let's get rid of the revolutions there by writing once again that there's 2 pi radians in 1 revolution. So look very carefully what you have here. The alpha will come out to be, I'll just sort of collect all the numbers out front here. I'll have a 10 times a 2 pi, that's that number and that number. And I have a 1 squared, that's that number. And I also have a 60 squared here in the bottom. So I've just collected all of the numbers together here in the front. Let's collect the units now. What I have here, I have a rev per minute squared. That's the original unit on the number right there. And when I square things over here, this will be a minute squared and a second squared in the bottom, because the minute squared there and the second squared there, you square the units just like you square the number. So there's the units right there. And also over here, what I have, now I have a radian over here, and I have a rev over there. So those are what all the units have become. So if I sort of look at what cancels what here, I can see very clearly that that revolution is going to cancel that revolutions. Here's that trick. Here's that needed trick here of squaring the term, because now the original minute squared will cancel the minute squared in the original problem there, in the original statement of the number. So what units am I left with over here? All these units just boil down to a radian per second squared, which is exactly what I want. Now you can get your calculator out and figure what this is going to be over here in terms of the numbers, but you'll get some big number here for alpha here, which will be in radians per second squared. So just to wrap up then, this has kind of been a long video, but just to wrap it up here once again, when we do linear motion, we have x, v, and a. When we do angular motion, we have theta, omega, and alpha. X is measured in meters, theta is measured in degrees, radians, or revolutions. A couple units going on here. V is often in meters per second. Omega should often be in radians per second. Acceleration is in some length per time squared. Meters per second squared typically. Well, alpha then will be in radians per second squared. So that's sort of the rundown for the whole thing. And also you have the F over here, which is in newtons over here. You have a torque over here, which is in a newton meter. And just one more bit of caution, which is sort of what this video is about here, is although we like to standardize on meters per second squared, and so on for x, v, and a, if you want to get some standardization in your own thinking about how this works, I would strongly recommend focusing on theta to be always in radians, omega to always be in radians per second, and alpha to always be in radians per second squared. So over here now, your radian is sort of like your friend, the meter in here. So if you sort of think about it that way, you can't go wrong. You'll sort of get everything to work out right. But sometimes in the beginnings of problems, you might have to take a few steps to convert things like revolutions per minute and things like that into the radians, so then you can get your problem to work out.